How does Helmholtz free energy explain confined chemical reactions? Have you ever wondered how chemical reactions behave when they are squeezed into tight spaces? The Helmholtz free energy is a key player in understanding this. It is a measure of the energy available to do work in a system at constant temperature and volume. This concept becomes especially important when we look at confined chemical reactions, where the volume is fixed. To start, the Helmholtz free energy is calculated using the formula. Helmholtz free energy equals internal energy minus the product of temperature and entropy. This means it takes into account how much energy is available after considering the disorder in the system, known as entropy. In confined spaces, reactions often occur at constant volume. This is where Helmholtz free energy shines. When we look at the change in Helmholtz free energy during a reaction, we can determine if that reaction will happen spontaneously. If the change in Helmholtz free energy is negative, the reaction is likely to proceed. This indicates that the system is moving towards a state of lower energy, which is thermodynamically favorable. Now let's talk about equilibrium. When a system reaches equilibrium, the Helmholtz free energy is at its minimum. This means that the reaction has settled into a stable state. In confined reactions, this helps us predict what the final amounts of reactants and products will be. Entropy plays a big role here too. In confined spaces, the movement of molecules is restricted. This can lead to significant changes in entropy. The Helmholtz free energy helps balance these energy changes with the effects of entropy. This balance is crucial for determining whether a reaction will happen or not. Another interesting aspect is how Helmholtz free energy relates to the maximum work that can be extracted from a reaction. In confined environments, where volume changes are not a factor, the Helmholtz free energy change directly corresponds to the useful work that can be done by the reaction. Finally, there is a connection to statistical mechanics. Helmholtz free energy can be calculated using partition functions, which count all the different ways particles can be arranged. This approach is particularly useful in confined spaces, where molecular interactions can greatly influence the outcome of reactions. In practical terms, this understanding is essential for reactions taking place in microreactors, nanopores, or even within biological cells. By using Helmholtz free energy, scientists can predict which reactions will occur, what their equilibrium states will be, and how much work can be harnessed from these confined systems. This makes Helmholtz free energy a vital tool in the study of confined chemical reactions.